Hello, everyone, and welcome to QJam 2021 set of talks starting from today. Today, we have only one speaker, but we'll have multiple speakers over the next few days as well. And hopefully, you will tune into these talks to get an idea of what kind of topics you can be participating in as part of QJam. So without further ado, let's get started. The first speaker today, we have Marcel Pfaffhauser from, I didn't pronounce that correctly, right? He's from IBM Research in Zurich. Marcel studied at ETH Zurich, initially in computer science, focusing on theoretical computer science. And after that, he's also worked as a Unity developer for 5 years, working on gamification. And since last year, he's been at IBM Research in Zurich, working on quantum education team together with James Wootton. And today he'll be talking about playing and creating games to learn quantum computation. And so with that, Marcel, you can share your screen. I'll stop sharing.
Thank you, Gibran, for the introduction. So today I will just want to show you several different tools, or more or less games, which we use to teach, or which we tell people they can use it to learn quantum computation. Some of these tools were created by ourselves at IBM in Zurich, or at other places. The first tool which I want to show is called Quantum Odyssey. It's a game, a learning application, and it's created by Quarks Interactive, but they are in cooperation with us from IBM. We gave them some feedback on it. And we just want to make this tool into a proper learning tool. So first, what is this? Quantum Odyssey is a puzzle game. So you learn quantum computation here by solving puzzles, and these puzzles all use quantum computation. So let's first start with the editor, where I can play with the right and show you how this represents quantum computation. Sorry, still loading. So what we can here see is a different representation on quantum circuits than you may normally have seen. Here, what is going from top to down, these balls are a representation of the probability amplitudes that for a given quantum circuit. So here we can see the 0, 0, 0, 1, 1, 0, and 1, 1. These are possible states for, or possible measurements or final states for a 2-qubit system. We always assume in this game, or also in, for example, in Qiskit, that the basis state is all 0 states, so where all qubits are in 0. And what we can build here is we can build a circuit, and the way we do it is we apply gates to our qubit. And what I did here is I applied the X gate, which is kind of similar to a NOT gate in classical computation, which is applied on the first qubit. I can also apply it on the second qubit. And this editor here can be used to actually create puzzles. And these puzzles can, for example, be shared with other students, or if you are a teacher at university, shared with your students. And the puzzle is always, you can see on the bottom here, a state which we want to achieve. For example, here the state which we would want to achieve is the 0, 1 state, and now we would need to apply gates to get it. And of course, here we can already see it. We apply just the X gate, but when we go to the menu, we can see that in the actual puzzles, this will look a bit different. I prepared some puzzles for today, not the first 3. So just to show you how some simple puzzles can look like. So what we have here is we have a circuit, and here we have an Hadamard gate applied to the qubit. So we have only a 1 qubit system. Here a Hadamard gate is applied, but we actually want the qubit to be in the end in the state 1, not in the state 0 as it is in the beginning, and also not in the state 0 plus 1 divided by square root of 2 as it is here. So a puzzle for you or a student would be, how can we make out of this state which we have here, which we can change, state 1, which we want here. And here we can see that this tool actually uses gamifications, like here it is explosions, to introduce how different probability amplitudes cancel each other out. A red ball stands for a negative amplitude, a blue ball for a positive one. So when the red and the blue ball collide, they cancel each other out. And when 2 blue balls collide, they get added up. And so, of course, what we can do here is just reverse this H gate, which we have, get in the state 0, then apply an X, and of course get the 1. And this is, for me, one interesting example, because quantum mechanics here, quantum computation, is used as the game mechanic. And so for one thing, so this is interesting if you want to maybe create your own game. But it's also interesting for people who want to learn about quantum computation, because you can just play games or here try to solve these puzzles, and by this, learn more about quantum computation. You will get some intuition about it, and you will also be maybe able, let's, sorry. Okay, now it works. Do a bit hard puzzle, show you a bit more what you can see. So what we want to achieve here is we want to have our qubit system in the state 0, 1 minus 1, 0. So the red ball shows that we want to have it in the minus state. What we can see here is that we have here a Hadamard gate followed by a controlled X gate. So we know that these 2 qubits are entangled. And we can also see it, that they are tangled because we have an asymmetry split here in the, on the left is like the first qubit, on the right is the second qubit, and they behave differently. We have 0, 0 plus 1, 1, one of the Bell states, and this 0, 1 minus 1, 0, which we want, would be another Bell state. Now the question would be how one can achieve this, and some ways to do this would be just to play around a bit, example like this, and we can see, okay, this is kind of looking correct, but not completely. So we now also want to look, okay, which state do we have here? So we know here on the bottom these gates are applied. So then we also know, okay, we actually want to be the ball in this part here. So when a ball would be coming down from 1, 1, we could see here, it would get split from the Hadamard gate into a negative, into a positive amplitude here for the 0, 1 state, and a negative amplitude here for the 1, 0 state. This means that before this circuit is applied, we want to apply 2 X gates. Now you can see the 2 X plates transform the 0, 0 to the 1, 1 state. And now here we are in the correct place, and yeah, we got it correct. I will just show one puzzle more before I show a bit also different tools which we use, just to show you a bit, why we think this tool is interesting and why this tool can be used to learn quantum computation. And yeah, here we can see a really lot of stuff is happening. And actually, here we don't even know what kind of gates are applied. We just know, okay, we have a state here which is a superposition with all qubits, but we have 2 negative amplitudes here. So what we might think that to reduce this state, we will need some Hadamard gates, because we need this for the superposition. And when we try this, okay, we can actually see, well, we have now less states, but still more than just the 0, 1 state, as the whole 0 state. So before applying all this Hadamard, the question would be, what do we want to do? So we can see here that in the case of 110 and 111, we have negative amplitude. So what we might want is maybe apply a set gate, but we want to apply a controlled set gate. And what we can see now is that only when the first qubit is 1, we apply a set gate, and what the set gate does is it applies a negative phase to the second to the second qubit. So we are now in the superposition state with all positive amplitudes afterward. And of course, here we can apply the Hadamards to undo the superposition again. And when that happens, we go back to the 0, 0. So what we can see here is that trying to solve these puzzles, we can either use pre-knowledge, which we have from quantum computation itself, or we can also use this different kind of visualization here that we can actually see, okay, these 2 lines are red. What kind of gates do I need to apply to actually influence them? So I think one reason why quantum odyssey can really be useful is because it just has a completely different visualization than you normally see with quantum computation. And in general, when you have different visualizations, it helps you to get a better understanding and to just get some kind of intuition about it. So this was one tool. Sorry, I share again. I don't share my whole screen. So, this was one tool how you can learn to actually do quantum computation by playing games. But what we also have is several other tools. They are on our GitHub page. For example, we have Qiske, which is standing for a small game engine where we can use Qiskit, the programming language from which is used in Python for the IBM Quantum computers to program, and we can use this to try to create a computer game. So why should one use Qiskit or in general quantum computation to create computer games? One reason would be to learn quantum computation, and another reason would be maybe we can really make some interesting properties or interesting effects which are quantum, can be used for a computer game. And one possible aspect there would be, for example, quantum procedural generation. So we use some qubits or some quantum algorithm to do procedural generation to generate worlds for a computer game. So here we have just a really simple example. So what we generate here is a kind of a 2D world, which is filled with trees and some plants and also some lakes. And when I now start it again, it takes a while, you can see that it looks quite different. So what we do here is we generate a random landscape, which is not completely random because as you can see, all these parts are kind of making sense. You don't just have like one tile of this lake in the woods or one flower just in the middle of the lake, but we have actually, something coherent, which could serve as a world for a small computer game. And I am playing this now inside from Unity, which was created to make Qiski, but you can actually also make a build. This means you, on a Windows computer, you make a .exe file where this would run inside. But what we try to achieve here is that actually you don't need to understand Unity in order to program this game, but instead what you will program is you can use Python, the programming language which is used for for Qiski to access the IBM quantum computers and program the whole game inside here. So you will see here some typical Qiski code. What you see in the beginning is, I'm not sure how familiar you are with Python, but we import here micro Qiski. Instead of micro Qiski, one could also import the whole Qiski framework, which has a lot more inside it. We import here micro Qiski because it just is enough for what we want to do here. So just to show how simple is, or how we try to make this game engine simple is, here in the beginning we just load some images, and we have here these images, and when we go back to Unity, we can see these are just these images we have here. So this whole game or this demo which you saw before, this can be all done by just using one Python file and this game folder, which is called game, and putting just all the assets for visuals. Here it's for the terrain types inside this game folder. So you don't have to use Unity, but instead you can really, in reality, just open this one folder here, and inside this folder access this Python file, which is called game.py, and just manipulate this in order to create your own game. In case you're wondering, the green signs just means it's checked in, and the red sign means I've changed something in this file. But don't worry about it. Nothing is broken. Everything works. So I mentioned before that we want to use procedural generation with quantum computers to generate game worlds. And this is exactly what we are doing here in this first simple example. Namely, we make a quantum circuit here, which has one single qubit on it. And this is all we use to generate this whole world, one single qubit. So we take this qubit, then we define some angles, which we justify here. These are just some starting angles, and then we apply rotations to our qubit, namely an Rx rotation, or Z rotation, or Y rotation. So we rotate the qubit in in this direction and with these angles we have before. And then, so we get here an X and a Y as inputs. According to them, we generate these angles, and then we simulate the probability that this qubit gets as outcome 0. So yeah, here we calculate the probability out of it. These two probabilities with, and then what we then do, this probability will be somewhere between 0 and 1, as you can assume, because all probabilities are this. So we do these rotations, which are dependent on the X and Y coordinate. These are the X and Y coordinate in the world. So for example, the coordinates of the one tile on the bottom of my screen, on the left bottom of my screen, this one would have the position 0, 0 in the world. And this one would be 1, 0, 2, 0, and so on. And when we move around, we change the whole screen. So we see a lot more different sprites on different positions. And yeah, and then we apply these predefined rotations according to this position on the screen. We just define something here. So if you want to build something like this, you can look at our code and use the same. But in the end, we want just to apply some rotations which are dependent on X and Y coordinates, which are here. Then we apply these to the qubit, to the one single qubit, and then we measure the qubit and get this probability. And depending on what the outcome of this probability is, between 0 and 1, we choose which terrain type this gives. So here above, we defined this. So if the probability to be, so we can see here we have these 7 different images. One is double, but that's something we wanted. So if the probability that this qubit is 0 is between 0 and 1/7, then this terrain will be chosen. Between 1/7 and 2/7, this will be chosen, and so on. And this one, the 3, is chosen if the probability is between 1 and 1 - 1/7. So why do we do it this way? The reason is because we get a coherent landscape. Because we just rotate these qubits according to the X and Y coordinates, this means that even though we have a kind of random rotation in the beginning, places which are next to each other will have a similar probability. So we have this kind of border. So inside here we have all the spaces which have where with these rotations applied, the probability is somewhere between 0 and 1/7. Then here on this border, it will change from 1/7 to 2/7 and so on. And from this, we get this more or less consistent world. And as I said, this is just a really, really simple example on how one can use quantum computation to make a game or to make procedural generation. And we really made this small Qiskit game engine to make it as simple as possible for people. So so the whole well, game is a bit more, but the whole process here is really just these lines long. We define which images we want. If we define this function depending on the X and Y coordinates to say which of these images we want to have here. And then here, this is the code which happens in the beginning. So we have kind of similar structure than Unity, if you know it. We have one function which gets called in the beginning to prepare everything. So in the beginning, we just do a random, we choose a random seed. And then depending on this random seed, which will be later used, we generate the whole landscape from the beginning. And then we have here a next frame function, which gets called every frame, every time the screen is new drawn. And here we just look if the player pressed an input for movement. If this is the case, we change our position X and Y here. This means, yeah, we walk around. So these are the default operations. And then again, we calculate the for each point, for each square on the screen, we calculate which sprite we want to have here. So we make these sprites here according to the image ID, according to these coordinates. And here from the coordinates, we have this position Y and X and Y, which is where the player walked. And this is just where we loop over, so the size of the screen if you want, as you can see here. If you Google for Qiskit and Qiske, or I can post the links afterwards in the chat, you will find the GitHub, which has this whole game engine, where you can also make more example, and which includes this really simple game scenario here. We plan, or we are even working on at the moment, on some new examples which are a bit more in depth, with step-by-step where you show how you can use this Qiskit, this Qiske and Python to program your own games. So in some months, if you search for them, yeah, you may find them. Why did we make this kind of tool? The reason is quite simple. A lot of programming is taught by people how to program simple games, because it's just a lot of fun for people. So for this reason, we just want to create some really simple environment where people can, without having much knowledge about game engines and how all these things work, to create simple games, or just simple visuals using quantum computation. But we also have some other tools. So this tool is meant for people who actually know Python or want to learn Python, and maybe even know our programming language, the programming language Qiskit already. But there may also be people who might know Unity, for example, a bit better. And for them, we also created a small, as you see here, this micro Qiskit is ported to a lot of different programming languages. One of them is Unity, or better C#, and it also works in Unity. And what you can see here is it's called Quantum Blur Unity. It's also on my GitHub page. I link it afterwards. A tool which allows to use really, really simple effects, which are quantum based, without having to know much about quantum computation. So what we are actually doing here is we take an image, any input image. Let me take this image here. And then what we do is we encode this image as a quantum circuit. And then in the quantum circuit, we apply a quantum image processing effect on it. In this, which we called here quantum blur. But what we do is we take this image here, interpret it as a quantum circuit in the way that the the colors, the brighter each pixel on the image we represent as one possible outcome of a quantum circuit. For example, the pixel right on the bottom would be the outcome being all zeros for a quantum circuit of size, which depends on the image. And the brighter the pixel is, for a grayscale image, or for this colored image, we do it for each color channel separately, but the brighter the pixel is, the higher we say is the probability that the outcome of that quantum circuit will get the all zero state. And this is just done for all images. So yeah, and in the end, what we really do is we encode this whole image. Then we have a full quantum circuit, which is has dimension. So if we have a 512 by 512 image, we use 512 is 2 to the 9. So we use 2 to the 9. We use 9 qubits to encode one dimension and 9 qubits to encode the other dimension. So we just need 18 qubits to encode this 512 by 512 qubit. This gives us exactly this 512 by 512 different possible outcomes when you measure this quantum circuit, which would represent to all the coordinates on this image. And after we have this, this circuit, what we do is we apply a rotation, which when I do a zero rotation, we see, okay, this is just the original image. And if we apply bigger and bigger rotations, you can see that the image is less and less recognizable. So what we do here is we use a quantum image processing effect. And this can be interesting because one can use that for different scenarios. For example, here we have a really simple image of a cube, but as soon as I apply some blur to it, we get a more complex structure. Let me take this cube and change its size a bit. So we have now a big cube. And as you can see, from this really simple original image, a cube with applying a simple, interpreting it as a quantum circuit, applying a simple rotation to all qubits, and then calculating it back, we can get some quite complex images. And these kind of images can, for example, be used for procedural generation. We could use this to generate a landscape with these kind of with this height map. For example, if you know Unity, and you know in Unity you can generate terrain just from small maps which show where the terrain has which height, and we can do something like this. And not, something else we can do is when you have games, something which is important is that you want to have different kinds of textures. So often in a game you have, as we've seen before with the example here, I mean, this here is a bit more abstract, but if you have more realistic games, you want to have some kind of ground which looks like grass. And one way to do this is, of course, have an artist and paint it all by himself. Another way would be to have a photographer to take a lot of different photos and then make sure that they are tileable. But what can also be done is, for example, take a simple image like this brush here, and then use some image processing effect to make different kinds of ground texture. So here, when we just have the image of the brush, we see, okay, it doesn't really look like ground. But the nice thing is with, for example, the quantum blur effect, and apply some kind of blur to it, it will look less like this original brush, but it looks more like a typical ground structure. And by applying different strengths of rotations, we can get slightly different looking grounds. And these textures, like example, these which I produced here, these were both produced from the image you've seen before with using this blur. These images could now be used in a game or maybe in some other way, to actually use some quantum procedural generation in making your game. And also, as mentioned, this example is quantum blur can be downloaded, and this is another way how people can learn about quantum computation. So our first was we can just play games to learn a bit. The second was we can make really simple games like here by using some simple quantum generation and using some simple procedural generation, or just program some other way with Qiskit. And here is another more advanced way which you might want to use in the future, where we take some quantum algorithms, for example, this blur image processing effect, and apply it to different kinds of things, like some seed images for procedural landscape generation, or on some nature pictures to make some textures for your game. So we can see, one can use applied quantum algorithms already to some interesting, or maybe some even useful, fun things. And I say quantum software here because, as mentioned, this whole process here is made with a quantum simulator. So this is not run on the real quantum hardware because it just runs on my computer locally. But this image processing effect, which we see here, is only possible with a quantum simulator. We can't get the same effect without having a quantum simulator. And maybe in the future, some of you might find some other interesting effects. For example, to just show this as a finishing touch, and you have this butterfly here, and in this script, which can be changed, we have also, you may see this button here, applying your own effect. And what this does is you can, in this simple script in Unity, define your own kind of quantum effect, which should be applied to the, sorry, it's a bit slow, which should be applied to the image, and maybe you find something interesting. So this is a completely different effect, which also was created by interpreting the image as a quantum circuit and then applying some gates on it. So here we can see what we do. So here we get this, here we translate the different color channels from the image into quantum circuits. And here we apply some kind of effects to these circuits. But here we apply a controlled Q to some fraction of them. So with so this just, if you go to the definition, you can see what happens here is we just apply a controlled X gate, a controlled X rotation. So we have a controlled rotation in the direction X on the qubits with the rotation, which is defined here, which is p half. And we apply this only to some parts of the qubit. Like on the red channel, we apply this only to every second qubit, starting with the first one. And on the other color channels, we apply it just to every, also to every second one, but starting with the 0th one. So, and yeah, and when we do this controlled X rotations, which is actually what they do is they will do some kind of flipping. So we have an X which just inverts the colors, but because it's controlled, it's not happened everywhere. So we have some rotations which partially take place here. And yeah, simple like this, you can maybe play around and find your own interesting image processing effects in the future, or maybe just use this as an inspiration to come up with your own ideas how to use quantum computer or quantum simulators to make interesting effects which could be used in art or also in making computer games or other products. That's for me. Let me just show do the link, paste links into to my GitHub. So this is the link to the Qiskit. To this small game engine, and when you look around, you find also other projects. Quantum Blur is this one here, and just to give you one example of what one can do with such a quantum blur. Actually, this week in Berlin, there will be an exhibition by a quite famous artist, Roman Lipsky, who created art using this quantum blur, a bit more advanced. He used quite a cool tool, but it was used on this. So yeah, one can use these tools to actually also generate art. And yeah, that's from my part. And feel free to ask questions if you have some.
Thanks very much, Marcel. As Marcel mentioned, please go ahead and put your questions in the chat. So Israel has a question. Are you using Q# in Visual Studio? Or are you relying on some Python binding?
No, there are different ways we use it. Do it in the example which I showed first with last with the quantum blur. There we use a quantum simulator which micro Qiskit, which is based on our actual Qiskit. So everything just runs in inside C#. We don't have any bindings. In the first example in Qiskit, what we do there is we have a whole Python environment with Qiskit installed, set up in our Unity project or in the build in the exe. And from Unity we call we make a separate thread which opens this opens the Python exe or the Python executable and gives inputted the game file, the game PI which you've seen. So we actually use Unity just for the visuals, and we have some communication between Python and Unity built in, and the Python files run on actual Python executable in its own environment, and that's how that works. If you're interested to setting up something like that yourself, we also did a really simple project called QCU, which just allows you to run simple Python files from inside Unity, and it has some instructions there on how you can do that. And this plugin was used to develop Kiske. So we first made this plugin, and we saw how it was done, and then we made this small game engine, which I showed before.
I was thinking that some of the transformations that you're using for the quantum blur effect, what would happen if we, let's say, change the Born rule to some other hypothetical rule for calculating probability? So, consider stronger than quantum physical theories, or consider some variation of any of the rules in quantum mechanics, and then apply that modified physical theory to these transformations.
Good question. Never thought on it. I think what could happen? I'm pretty sure new kind of effects could emerge. For that that we could actually do this, we would need to rewrite the software, because at the moment what it does is really it's used as a quantum circuit, and all the operations we apply are gates. So we will need to make the simulator be able to also handle these non-quantum gates. But yeah, what could happen? I'm pretty sure you could use at the moment, because it's quantum. The whole process is non-signaling. So what you could do with stronger effects could be that you kind of have signaling, so that like one part of the image would this already influences the other parts, but that it that information of one part could be encoded in another part in a signaling way, meaning that you have the actual information on it and not just a correlation. We really never tried this because we worked with the quantum simulator, but for the future that could be an interesting problem to do.
With the no-signaling theories, as well as just changing Born rule to something else, I thought also might be nice, right? So how does the probability weightage kind of, rather than L2 norm, if you're applying some other norm for calculating the probabilities, what's the visual effect that comes out?
So one thing which could happen is like, because the image is kind of used by like normalizing the probabilities. So if you have more extreme probabilities for certain states or even wrong ones, what would happen is that less parts of the image would actually be visible, or you would have more extreme effects. For example, when you have really high probabilities just in single outputs, or just a lot higher than the others, these one get really bright, like almost white, and all the other pixels get almost black. So effects like this can happen. Yes, in the chat, what is the future of quantum games? We work together also with some other people working on quantum games, defining them and seeing what happens. So we see three kinds of possibilities with quantum games. So first ones would be games which are just inspired by quantum, which we already see a lot. But what we may see in the future more is games which were actually done using quantum principles. For example, Quantum Odyssey, which I show, has as a game mechanic quantum computation, just as the main game mechanic. But what could also do is to generate parts of the game with quantum in mind. Like quantum machine learning comes to mind for AI, but must not even be necessary. This quantum blur effect, which I showed on the image, which transforms image, actually this effect is at the moment used in a game for the AI. So they kind of try to use this kind of effect to influence the AI behavior. And they use this because they want to have something which has some kind of logic behind, but is actually nothing people are used to it. Like similar in the sense as this quantum blur, this randomness has its own distinct visuals, but it looks different, for example, to parallel noise, but it can be used in similar forms. So what could be interesting there is just to use these kind of quantum effects or algorithms instead of classical ones like parallel noise, because people get used to parallel noise. They know when something is created by that. And yeah, and one other big part for quantum games, I think in the future, when quantum becomes even more important, is just people make more games or more sophisticated games to teach people about quantum computation, like Quantum Odyssey, but we see a lot of them. Quantum Flytrap, the website is another one which I use quite a bit and which I like. And yeah, I think people will use gamification to actually explain quantum games to people. And yeah, just because Bill Gonzalez wrote something, if you're interested in it, here is a small article about the art which was generated with this quantum blur method. As I said, the exhibition will take place this week, and these are just some excerpts of the arts, but yeah. And I'm actually sitting at the moment in the kitchen of the artist who created this art. Yeah.
So yeah, thank you very much again I know you were really busy this week. So thank you again for taking time. Any other questions?
The language was called Quantum Odyssey. Quantum Odyssey was programmed in Unity as well, not with our tools, just separately, but yeah, we're in contact with them. It uses its own small language to store quantum circuits, but this language is compatible with QASM, and they can translate from their representation to QASM files, and they even can output the quantum circuits as a Qiskit file, or at least this will be the next version, which I already tried. But so the idea there is that you can actually use Qiskit code and see this circuit which is constructed in Quantum Odyssey. Or you can use Quantum Odyssey to construct a circuit, and because it may be better for you to construct it using that tool, and then produce Qiskit code from it to actually run it on real quantum hardware from IBM Research, or from IBM Quantum. Yeah, it's not also used as a learning tool, but also kind of as a visual editor for quantum circuits, which is compatible with Qiskit.
Any other questions?
And if you want more info about Quantum Odyssey, here is a link to the Quantum homepage. At the moment, it's only it can be bought from their website. It will be coming at some point to Steam and some other platforms, and maybe some high schools will also get access to it, but it's still kind of in a beta and further developed.
No other questions. We'll thank our speaker, Marcel, again. Thank you again, Marcel, for taking the time out. And if you're okay with it, if any of our participants are interested in working during the next week in QJam on game-related project, probably we'll kind of reach out to you if you're available.
Yes, of course. Feel free to reach out to me. I'm always happy to see game jam and hackathon projects with Quantum, which are interesting. So yeah.
Thank you very much. And to everyone else, just a reminder that we do have lots of other talks coming up in the next 2 days. So Wednesday, we've got talks on error mitigation, very much like today's talk about music generation via quantum computation, quantum shots video on Quing. This video you can actually kind of watch already online. So just Google Quing. our Quantum Programming Challenge website on hack.ai, Quantum Steampunk on Thursday, and finally developing collective explanations on Thursday. And then finally, formally, the QJam will kick off on Friday. So hopefully we will see many of you in the next few days. Thank you again, Marcel, and thank you everyone else. And we'll see everyone tomorrow. Bye. Thank you.